Okay, well, let's go and get started for today. So, in terms of announcements, Quiz 9 is going to be due on Wednesday night. I would wait a little bit. We're still covering some material to cover all the questions on that one. I said I was going to post a problem set today. I'm not going to be able to do that until Wednesday, so that problem set I'll put up on Wednesday. It'll be due the following Wednesday, so I'll give you a whole week to do it, okay? All right, we are 2 weeks away from our next exam, okay? So keep that in mind. That next exam is going to cover essentially Lecture 7, Lecture 8, and Lecture 9. So by the time we get done with Lecture 9, there's quite a bit of material in Lecture 9. We should be ready to take that next exam, okay? All right, so let's do this. Let's do our riddle, and then we'll jump into the material. So iron roof and glass walls, burns and burns but never falls. What is it? A lantern, exactly right. A lamp or a lantern. Yeah, see? Okay. All right, I know. They get worse and worse. Okay, so we left off right here on Friday. We had just really started into Lecture 9. The topic of Lecture 9 is oxidative phosphorylation. Oxidative phosphorylation is one of many processes in biology that can be described by this chemiosmotic model. So generally speaking, and this is again a very broad view, 5,208-foot view of the chemiosmotic model, but generally speaking, you have some reduced electron carrier or donor that's going to give electrons to some respiratory chain or electron transport chain that's going to pass electrons to then some final electron acceptor. Those processes are typically exergonic. That will lead to the translocation of protons across the membrane, leading to a pH, which is called a pH gradient or proton gradient. And then those protons can be then reabsorbed by whatever compartment they are pumped out of to drive some process. Okay. For oxidative phosphorylation, being more specific, our reduced electron donors are going to be NADH primarily, but also succinate/FADH2 is going to also contribute electrons to this process. Oxygen in mammalian systems is going to be our terminal electron acceptor. Okay, and then protons being reabsorbed by mitochondria are going to lead to ATP synthesis by this molecule ATP synthase. Okay, our job in Lecture 9 is going to be go through each of the complexes in the respiratory chain or electron transport chain, and also structure and mechanism of this molecule ATP synthase. Okay, right. You know you're a nerd when you have a favorite molecule, and ATP synthase is my favorite molecule. Okay, so I mean I'm just telling you right now, that's kind of a geeky thing to say, but okay. I mean, maybe you have a favorite molecule, you can tell me about it later. Okay, and a favorite organelle, I was really pressed on a favorite organelle probably because ATP synthase mitochondria would be my favorite organelle. Okay, again, that's a very geeky thing, but hey, I'm okay with that. All right, now I got a question for you. We'll start today off considering this. We'll start with this question, okay? I need to expand it before you can see it at all. There we go. All right, so according to the chemiosmotic model, the thing that we were just talked about on Friday, the electron transport chain, ETC, and ATP synthesis are codependent. All right, why is the electron transport chain dependent upon ATP synthase? So by codependent, I want to make sure that I describe that before we go any further. Sometimes we'll say that these processes are coupled, meaning the electron transport chain can't run without ATP synthase, and vice versa. ATP synthase can't run without the electron transport chain. Okay. I think it's fairly obvious why ATP synthase can't run without the electron transport chain. You can't make ATP without a proton gradient, and the proton gradient is established by electron transport chain. Okay. But why is it the reverse true? Why do you have to have ATP synthase, making ATP, to carry out the process of electron transport chain? So talk to your neighbor about that. I'm going to give you 2 minutes to text me an answer, and then we'll look at this together as a class. On your marks, get set, go. What do you think? Okay, text me an answer. Talk to your neighbor. Why is that the case? Okay, about 20 seconds left. So submit an answer if you haven't done so. All right, submit an answer. Quickly, 3 seconds. All right. Let's go ahead and check this out. Okay, so to keep the flow of protons at steady state, maintain the electrochemical gradient. Okay, ATP synthase maintains the charge proton gradient necessary for electron transport chain to function. E.g., electron transport chain is only favorable in specific charge environment. Okay, hitting around the answer, I think, because ETC requires a proton from ATP synthase. That's actually not true. The ETC uses ATP for substrate level phosphorylation. No, that's not true. ATP synthase pumps the protons back to in so electron transport chain can utilize them. You don't actually run out of the proton, so that would not, I mean, you're hitting around the answer, but not quite. ATP synthase transports protons into the inner membrane. Yes, that's true. But why is that important? ATP synthase brings protons into the mitochondria, which are used to power ETC. So what powers the ETC is actually redox reactions. So not powered by these. Without ATP synthase, the proton gradient would be destroyed. It wouldn't be destroyed. ATP synthase creates the concentration gradient for ETC. No, the ETC creates a concentration gradient for ATP synthase. Let me keep reading here. The proton gradient will be rebalanced if ATP synthase wasn't present. That actually is close enough. Let's do this. All right, so the proton gradient won't be rebalanced if ATP synthase wasn't present. Depends on what is meant by rebalanced, but this is hinting at the right answer. So let me go ahead and go back to our slides here, and let's look at this in a little bit more detailed level. Okay, so what you're looking at here is oxidative phosphorylation, essentially, and let me go ahead and highlight this. Okay, all of this that you see here, okay, essentially I'll draw a line there. Everything to the left of that, that's the electron transport chain. Okay, we've got the P side here. That's where protons are going to be pumped. And you got the inside in here. Okay, P side, remember, is inner membrane space in mitochondria. The inside would be the matrix of the mitochondria. Okay, and then each of these colorful things would be the three-dimensional structure of each of those complexes. Complex 1, 2, 3, and 4. We'll look at those in more detail moving forward. All right. When we look at this, and this is going to be important to try and to answer that question that I just asked. All right, when we look at the movement of a proton, let's say 1 mole of protons. Okay, so I'm just going to put the number 1 here. Okay. To move a mole of proton from inside to P side is going to cost 21 kilojoules of energy. Okay, and this would be 21 kilojoules per mole of protons. Right? That is dependent upon really 2 factors. It would be dependent upon the difference in pH of the 2 compartments. So the P side, because it has more protons in it than the inside, is expected to have a lower pH. Okay, the difference in pH between the P side and the inside. Whoa, what happened? There we go. I rotated. Okay, so but the difference in pH between the P side and inside is about 0.75 in a healthy mitochondria. Okay, 0.75 pH units. The membrane potential also determines that number. Okay, this 21 kilojoules per mole. Okay, membrane potential is about 0.15 volts. It would be positive 0.15 volts, okay, for this membrane. And that will determine how much it costs to move a mole of protons from inside to P side. Those factors start to change, the difference in pH between them and the membrane potential, then that value could go up or down, okay, in terms of cost. Now, let's look at it from this standpoint then, starting here. Okay, we'll just start with NADH. NADH is going to contribute 2 electrons. So It's going to have 2 electrons here. It's going to contribute those guys. And those guys are going to go through complex 1. We'll look at that later on. And they'll make their way to complex 3. Now, when they go through complex 1, okay, they lead to the translocation of 4 protons. Okay. Those same protons now are going to make it through complex 3. Okay, and then go through complex 3 and arrive at complex 4. When they do that, they'll lead to the translocation of an additional 4 protons. Again, tracing these 2 electrons through complex 1, through complex 3, and then finally, once they get to complex 4, they will be given the oxygen, which is our final electron acceptor, making water. And when they do that, they will lead to, again, the translocation of 2 more protons. So if we add these together, 4 protons from complex 1, 4 protons from complex 2, or 3, I'm sorry, and 2 from complex 4, that's 10 protons total. Right? That's moved by electrons going from NADH to oxygen, 2 of them. Okay? They can lead to the movement of 10 protons. To move 10 protons, we just take 10 times 21 kilojoules per mole, because 1 proton can be moved, or it costs 21 kilojoules per mole to move 1 proton. To move 10 would be just 21 times 10. So this is going to cost, right, to move this, it's going to cost 210 kilojoules. Okay? Now, let's come down here, okay? And we're getting to our answer here. When we start to look at the energy available in moving electrons from NADH to oxygen, we can calculate the delta G of that process. It's just a redox reaction. There's lots of complicated steps in it, but as a whole, it's just the movement of 2 electrons to oxygen, okay? And we can calculate the delta G of that reaction. Delta G at standard conditions is equal to negative NF delta E. Okay, N is the number of electrons being moved, so this would be 2. F is Faraday's constant, 96.5 kilojoules per mole per volt. Okay, and then finally, delta E is the change in the reduction potential, and that's what I want to spend our time thinking about. The change in the reduction potential is essentially the reduction potential of our electron acceptor minus the reduction potential of our electron donor. Chills of excitement just went up and down your spine because you are starting to remember general chemistry. And you're seeing like images of batteries pop into your head, right? Okay, that's essentially what's going on here. Okay, we're just talking about redox chemistry. All right, in redox chemistry, the change in reduction potential of oxygen, in this case, because that's our electron acceptor, minus a reduction potential of NADH, because that's our electron donor. Okay, well, here are the values for that. Okay, 0.82 volts is the reduction potential of oxygen. It's a strong, what would be considered oxidizing agent, one of the strongest oxidizing agents in biology, right? NADH, so this is for oxygen, right? NADH's reduction potential is really low, negative 0.32 volts, okay? Doing the arithmetic, and we're not going to do it, I trust that you could do it on your own, but doing the arithmetic, the delta G of this reaction using this equation would be negative 220 kilojoules per mole. Now notice what I said up here. I said you need to move electrons, moving electrons from NADH to oxygen, you're going to pump 10 protons, you need 210 kilojoules per mole. Okay. Well, there's 220 available, that's a good thing. Okay, we're not breaking the first law of thermodynamics and looking at this process. Okay, we're not creating or destroying injury. However, right, when we start to look at our question, okay, if this other process, the process over here, ATP synthase, if this is shut down, then what happens is the electron transport chain runs for a little bit, and these values, the difference in pH between the 2 compartments, as well as membrane potential, start to increase because they keep pumping protons, but nothing's bringing them back into the matrix. And so gradient becomes too steep, there's not enough energy in this to keep moving protons into the p side if you don't have ATP synthase. Okay? Now I said, remember my question was, well, why is the electron transport chain dependent upon ATP synthase? Well, that's our reason. Because, and going back to the answer that I highlighted, the ATP synthase essentially balances the proton gradient. It's something that allows the protons to come seeping back into the inside to ensure that it doesn't become too steep. Okay? Question, yes?
Where did the rest of the energy from that reaction, is it just dissipated as heat or something?
Yeah, yeah. So the question is, where would the rest of this energy, only about 10 kilojoules worth, go? Because you're spending about 210, where would it go? It's going to be dissipated as heat. Yeah. So, you know, second law of thermodynamics dictates that we're never going to get the full amount of energy. We're always going to be losing some. Okay. And so we lost some to essentially heat. In this case, would be entropy. Yeah. Okay. And that's why our bodies are not at room temperature. Okay. If they are at room temperature, then that's not good for you. Okay. I mean, you probably won't know it, but other people around you will. Some of them will be very sad at that point in time. Okay. All right. Questions? It's morbid, right? Yeah.
What does NADH deliver its electrons to?
We're going to look at that. Yeah, it's a great question. So the question is, what does the NADH deliver its electrons to? So what we are going to do really for the rest of today and Wednesdays, we're going to start to look at, you know, these lines that I drew going through these complexes. And we want to look at, well, how do electrons, first of all, get delivered to complex 1? How do they make it through complex 1? And then from complex 1, how do they make it to complex 3? And then once they're at complex 3, how do they make it through complex 3? And then once through complex 3, how do they make it to complex 4? And how do they make it, once they make it to complex 4, how do they make it through complex 4? And why do they skip complex 2? And what's complex 2 all about? Right, these are all good questions. I'm sure that all of you are sitting there thinking to yourself those exact questions. And I'm glad that you were thinking of that, because we need to talk about each of those things. And we're not going to go into like real gory detail, but probably more detail than you've done in many of your other coursework. Okay, so we are going to do that. So that's our job, looking at essentially the redox reactions required to move electrons through the complexes. Okay. Other questions before we make that our main task of the day? Okay. These two processes, as a take-home, are coupled. Right? And there's good reasons why we say that they're coupled, and there's good experimental evidence that they are indeed coupled or codependent. Okay? Now, let's move on here. I've already asked that question. That was the question we were just looking at. And we want to start to think about, well, how do electrons get into complex 1 and then move through complex 1 and then on to 3 and 4, like I've already said. But to do that, and before I do that, I want to just make sure that we're all on the same page with the redox centers or the electron carriers that we're going to encounter in each of these complexes. And by that, I simply mean the things that are going to accept and donate electrons one to another. So we'll look at those first, and then as we encounter them in the complexes, you can refer back to them mentally and also, of course, in your notes. And the first one that we're going to look at is NADH. Okay, so this is really what would be considered an electron carrier. Carrying electrons from glycolysis, carrying electrons from the citric acid cycle, carrying electrons from fatty acid oxidation, carrying electrons from amino acid oxidation to the electron transport chain. Okay, and we, of course, have talked about NADH and its production in at least the citric acid cycle and NAD+. We never really looked at the molecule, though, and so I want to go ahead and look at the molecule right now. NAD stands for nicotinamide adenine dinucleotide. Dinucleotide meaning there's two nucleotides here. I could cut this in half. Okay, we have an adenine nucleotide in the bottom and then a nicotinamide nucleotide above that. Okay, so two nucleotides in this. Nicotinamide adenine dinucleotide. The oxidized form, NAD+, we call it NAD+ because it has this positive charge on that ring in the second nucleotide, nicotinamide nucleotide. Okay. That's where we get the term NAD+. That's the oxidized form. The reduced form, and the business end of this molecule, okay, is essentially this, okay? I've added a proton here, and that's the reduced form, NADH, okay? Now, this is the arrow and the things feeding into the arrow between the reduced and the oxidized form, a little bit deceptive. Let me go ahead and do this. Get rid of that. It is 2 electrons, but the electrons come on a hydride anion. Okay? And then there would be another proton that's kind of a spectator proton in this whole thing. That would be H+. Okay? And so you will see this then, this proton here ends up being that guy right there. Okay? It's not really a proton, I'm sorry, the hydride anion. It's carrying the 2 electrons. Okay? And then there's this other proton that comes along with it, and you've probably, I hope that you've noticed that in our equations, whenever we are talking about a dehydrogenase that uses NAD+, we'll see something like this. For instance, we could have glyceraldehyde 3-phosphate plus NAD+, goes to 1,3-bisphosphoglycerate plus NADH plus a proton. And we always have that plus the proton. And the reason is because these dehydrogenases, when they carry out their reaction, there are 2 protons or 2 hydrogen atoms that are always taken off of the reactant. One of them carries the 2 electrons and ends up on NAD+. The other one just is released off in the solution. Okay, and that's the H+. But it's 2 electrons as a total. Okay? But that's NADH, NAD+. Okay? Now I will say this last thing here before we go on and look at our other ones. Okay? This delivers 2 electrons at a time to complex what? None of the other complexes. NADH brings the 2 electrons to complex 1, dumps them off 2 at a time, and then leaves. NAD+ will be generated. It'll go on and pick up electrons from other carbon sources, right, in some other process. Okay? Questions on NADH, NAD+? How it gets this hydride anion, where it comes from, that would be dependent upon the reaction, okay, that we'd look at. Now, next one, I've got several of them on here actually. Let's go ahead and focus in on the left side of this. Okay, I've got to zoom in on this. There we go. Okay, FAD and FMN. Let's talk about FAD first. FAD stands for flavin adenine dinucleotide. Okay. That whole guy. Again, a dinucleotide, meaning there's 2 nucleotides in it. Okay. One of them is an adenine nucleotide. This would be adenine down here. So if I cut this in half, that would be the adenine portion of this. The other one's a flavin nucleotide, everything above it. Okay. And it's really this fused ring up here that's the business end of this molecule. Okay, FAD, the way we're looking at this right now, that's FAD, and that's the oxidized form. Okay. FAD can accept a single electron at a time. Okay, and it will come with a proton. And that's what's being illustrated here. You go in this direction, okay, it's getting this electron here, and it can adopt a radical form. what might be considered FADH. Oftentimes we'll draw a little dot to denote that it's a radical form. It'll accept the next electron, again with a proton, here. That would be the reduced, fully reduced form, FADH2. Okay. And it can go in the reverse direction. We'll go from fully reduced to radical to FAD. And radical is a chemical term. We're not talking about, you know, some extremist person, okay? Or when I was in the 80s, right, radical was the term that we used for, like, you know, I mean, I was a skateboarder, and so I was aspiring to be radical. I failed, I mean, usually. I wasn't quite like Tony Hawk, who was definitely radical, okay? That was when he was a teenager, though. I mean, I mean, he's still radical, I guess. It's just like me, though. He's an old radical guy, okay? Okay, anyway. I was an 80s kid. All of my pictures as an 80s, when I lived in the 80s, I got lost in some horrible burning accident. I don't know what happened. But I wore jam pants that are about, you know, and they're like polka dots, and I had turquoise shoes, Vision Streetwear shoes. They were awesome. They were radical. My brother had Vans, slip-on Vans that were hot pink and black checkers, and I wish I still had them because I could probably sell them online right now for a pretty price, but I don't, and neither does he. So anyway, okay. Questions about my 80s days? I've grown up. Did I have a mullet? No, I didn't have a mullet. I thought about it, but, you know, I was saved that unfortunate hairdo. But anyway. Start scanning the room. It's okay if you've got a mullet. You're okay. You're good. You're in good company. There's lots of people. Okay. Business in the front, party in the back. I know. I get it. All right. Now, we should return back to biochemistry. We really should. I mean, it's okay. Let's do that. Let's go back to biochemistry. Okay. FAD. Awesome. Radical. No, not awesome. Radical. Okay. For two reasons. Now, FMN. Let's just look at that real quickly here. FMN is this. Okay? Everything that I said with FAD would be true of FMN. FMN stands for flavin mononucleotide. Okay? In terms of chemistry, though, it can adopt a radical form, and then it can go to the fully reduced form. The thing about this is that FMN, that would be the oxidized form. We call it FMN. Oops. Here we go. The radical form of that would be this. I guess I don't have to draw it out here. It's already up there. And then, of course, FMNH2 would be the fully reduced form. Okay. Chemistry is essentially identical. It's lacking the adenine nucleotide in these. Okay. Now, I should say this because location of these are very different. Okay. FMN is found in complex 1. And it's only found in complex 1, okay, in what we're talking about in electron transport chain. FAD, on the other hand, is found in complex 2. Okay. They're not carriers in the sense that NADH brings electrons to the electron transport chain, gives those electrons, whoops, there we go. Gives those electrons to the electron transport chain and then leaves. The flavin nucleotides are immobilized within the complexes that I'm saying they're in. Okay, FMN never leaves complex 1 and FAD never leaves complex 2. Okay? It gets electrons from something that brings it to them. Okay? Now let's move over here to the other side of this. And we'll look at coenzyme Q. Let me zoom out a little bit so we can see the whole thing. Coenzyme Q, if you've been to a health food store, is CoQ10. Okay, they sell this as a supplement. Apparently it's good for your heart. I've never looked seriously into that. In the literature behind that, maybe it is, maybe it isn't. I don't know. Okay, but for our context, coenzyme Q, right, is a lipid-soluble electron carrier. It will carry electrons between complexes 1 and 2, 2, 3. Okay, so carries electrons from 1 and 2 to 3. Okay. The reason it's called coenzyme or CoQ10 is because it's got this group here 10 times. Very, very hydrophobic. Okay. You will not find this in the aqueous environment of the cell. It's sandwiched between the leaflets of the inner membrane of the mitochondria. Okay, in that hydrophobic environment. That's where you'll find it. Okay. The business end of the molecule is the ring form. Okay, and we call the fully oxidized form ubiquinone or Q. Okay, the none of ubiquinone refers to these two ketones. And that's the fully oxidized form. Just like the other two, the FAD and FMN, it can adopt a radical form. I'm not going to get distracted by the word radical this time. Some of you say you just did. Okay, it's getting worse. Keep on task, Aaron. Okay, anyway. Radical form, a semiquinone radical, okay, accepts an electron, accepts a proton, right? We call it the semiquinone radical, or QH. Okay, and then finally it can adopt, okay, the fully reduced form, ubiquinol. Okay, QH2 is what we'll refer to it. The nol, right, being the alcohols. Okay, hydroxyl groups. Nomenclature for this one can be confusing, and we're going to switch between it all the time because we're going to go from ubiquinone to radical form to ubiquinol, and we have to keep that nomenclature straight. I'd encourage you to try and remember that as we move forward, because this plays a very important role in transferring electrons through the electron transport chain. It truly is a carrier. It picks up electrons in 1 and 2, carries them on to the other complex 3. Okay. We'll also see it generated in other processes in the cell, and we'll talk about those when we get there. Okay. CoQ10, ubiquinone. Questions on anything on this page? Yes?
Does the ubiquinone and the ubiquinol names, does that just refer to the ring part, or does it also refer to the hydrophobic tail and the whole molecule?
Yeah, so the question is, does the ubiquinone and the ubiquinol refer to just the ring, or is it the whole molecule? It's the whole molecule, yeah. So the hydrophobic tail is really untouched in any of the redox chemistry. It's just part of the molecule. Certainly makes it hydrophobic, but it doesn't play a significant role in the chemistry that you're looking at here. Okay, so it just goes along with the nomenclature. Okay, now it can play an important role in terms of binding and binding energy to complexes, but beyond that, we'll talk about it. Yeah.
With these electrons, like, is it potential for them to be coming from NADH?
Yes. Yeah, and so we'll look at that. We'll look at the mechanism, but the question was, are these electrons, is it potential that they would come from NADH? And yes, they could. They don't have to. We'll see what they can come from lots of different places. But yes, they can come from NADH. Yep. Okay. Other questions? All right, radical. All right. Now, last slide here in terms of electron carriers and redox centers, okay, and here we see a family. There's actually 2 different families. Let me go ahead and cut the slide in half. Okay, let's look at everything on the left first, okay, and then we'll look on the right next, okay. The cytochromes, cytochrome refers actually to a protein that has some heme group in it, okay. And you're looking at the 3 different types of hemes that we would find in cytochromes found in an electron transport chain. Okay? There is what we call B-type cytochromes. Okay? And they have this ring. protoporphyrin 9, that actually is the heme group that's found in hemoglobin and myoglobin. Okay, but it can also be found in cytochrome proteins in the electron transport chain. Okay, so that's a B-type cytochrome. There is a C-type cytochrome here. Okay, structural differences are highlighted in these blue areas between cytochrome C and cytochrome B, or B-type and C-type. Okay, and then finally you would have A-type. Okay, and we're not talking about personalities here. Okay. A-type cytochromes, some of you that just went right over your head. You're probably not A-type if it went over your head, okay? But anyway, okay, you're like too relaxed, or you're just like, you know, he's so lame, I just can't believe it. But you've got me for another 7 weeks, so deal with it, all right? All right, now, A-type cytochromes, again, structural differences between B-type and A-type are highlighted in blue, okay? Now, you'll notice that in all of the cytochromes, okay, iron, 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 okay, those iron atoms are what's going to accept and donate the electrons. Of course, iron 2, this would be the reduced form, and iron 3, okay, would be oxidized. Iron 3 plus. And they'll alternate between iron 2 plus and 3 plus, depending on their redox state. Okay. They will accept, notice what we're saying here though, they're going to only accept a single electron at a time. They're not going to take 2 electrons, they don't adopt a radical form. Okay. They only accept a single electron and donate a single electron, which presents some interesting challenges to the electron transport chain. You got some things that give 2 electrons and some things that can only accept 1 at a time. And that's why I'm highlighting some of these radical forms. We'll talk about that as we move forward. Now, in terms of location, these B types are found really in complex 2 and 3. Okay? The C types are found in complex 3. And the A types are found in complex 4. Okay? Like the flavin nucleotides, these are immobilized. They're found in those complexes. They don't leave the complexes. They have electrons brought to them. So they'd be more like redox centers rather than carriers. And then finally, iron sulfur, and this, it says FES here. Let me put this, FES proteins, iron sulfur proteins. And these would be proteins that are found, again, in the electron transport chain, obviously, that have iron and sulfur found in them, okay? Much like the cytochromes, of course, we'd have iron 2 plus, adopting the reduced form, and iron 3 plus being the oxidized form. Okay? And what you're looking at down here, this would be just a variety of structures of iron sulfur centers that you'd find in these proteins. They can go from very simple, so this would be a very simple iron sulfur protein, and we call it FES, and that's it. Okay? It has an iron, and it's covalent, that iron atom is covalently bound to cysteine side chains in the protein, right? So here's the protein kind of highlighted in blue. Okay. You could have something that looks more complicated like this. We would call this Fe2S2, the 2 iron atoms here, and then there's 2 sulfur atoms here that are not part of, they're not coming from cysteine side chains, but then the iron atoms are also covalently bound to cysteine in the protein. You can go to something as complex as down here, where this would be iron 4, S4, and it's got this cubic structure to it. And there are 4 iron atoms, and there are 4 sulfur atoms in that cube. Okay? And then again, those are covalently bound to the protein by cysteine side chains. Okay. There is an iron 3, S4. I don't have it illustrated here, but can find that in electron transport chain as well. Okay. But these are, oops, I keep doing that. It's strange. I need to lock that. Anyway, sorry. There we go. But these are found in, and I'm just going to highlight here, these would be found in complex 1, 2, and 3. Okay. Now the temptation is to look at this figure and say, okay, well, which one, like where is Fe4S4? Is that found in complex 1, 2, or 3? Yes. Okay. It can be found, actually, I'm not sure if it is, I'm not sure exactly where, but these complex structures does not necessarily dictate where they are. For instance, you can have iron 2 S2 as well as an iron 4 S4 in the same protein, same complex. Okay. Now, complex 4 doesn't have iron sulfur protein, but I will tell you this. Right? There is in complex 4, we could cross this off and replace those with copper. And we would call it copper 2 S2, and that's found in complex 4. Okay. And so we'll encounter what's called a copper sulfur center in complex 4. And that's the parts. We haven't even started moving electrons around through complexes, but we've got the groundwork laid to do that. Are there any questions in this? Yes?
Are there particular amino acids that hold cytochrome?
Um,
I see in type C, it looks like there's some systems that are covalently bound.
Yep, so C-type is the only one that is covalently bound to the protein. Okay, and in that case, it is cysteines that will hold it in place. The B-type and the A-types are held by non-covalent interactions. And so you have a variety of different amino acids surrounding that site. I will tell you this, they're much like hemoglobin and myoglobin, they're dug deep into the heart of the protein to prevent water-catalyzed oxidation of iron. Okay, so they're in the hydrophobic core. I would have to check on this. I think with the A-type, there is an A-type heme that has a covalent bond to histidine at the iron atom, much like hemoglobin and myoglobin. I know that it has a histidine that's like a distal histidine because it actually binds oxygen. This is where oxygen will bind to receive electrons to become water. But I'm not sure if there's a quote-unquote proximal histidine on that, where there's an iron, covalent bond between iron and histidine. I'd have to check. Other questions? I got a question for you. We must have this question. Okay, so let's look at this here real quick, okay? So let me go here, pause that. Okay, so let's go back to the cytochromes. I want to use this to illustrate something here. Of the cytochromes, which group would you expect to have the highest reduction potential? A-type, B-type, and C-type, and why? Okay, tell me which one you think would have the highest reduction potential, and why would you think that based off of the information I've given you, okay? So a minute 43 to get this done. On your mark, get set, go. Let me go ahead and go back to, okay, the slide, and you can look at these. Which of these cytochromes will have the highest reduction potential, the largest reduction potential? Okay, all right, what do you think? Talk to your neighbor about that. A minute 45 seconds, or you did. Okay, what do you think? You have about 20 seconds left. So if you haven't submitted an answer, do so. All right. 2 seconds, 1 second. All right, let's check it out. See what people said here. Show results. A, okay. C, because it's most radical. Because it's most radical. Exactly right. Very good. You've been listening today. That's good. A-type, A, C. No one's picking B. It's like in the middle. B, oh, there's a B-type. B, less sterically hindered. Okay. A. I wonder if I can get the word cloud. Let's look at the word cloud here. Okay. Type. Of course. That doesn't help me out. Okay. So, so the answers seem to vary here. We're almost done with class. So let's just go ahead and look at the answer, or I'll give you the answer. So when we look at this, what I was hoping that your attention would be drawn to is the location of the heme group in regards to complexes. Okay. Generally speaking, and this is why I wanted to ask this question, okay, A-type is going to be the correct answer, and the reason is because it's at the end of the chain. Okay, as we move through the chain, reduction potentials of everything goes up. Okay, all right. So you have your lowest reduction potentials in complex 1. Okay, and then reduction potentials steadily increase in there, and the reason why is so that there's this constant drive to move electrons from complex 1 through to complex 3 through to complex 4. All right, it's essentially drawing electrons to the end of the chain. Oxygen is the terminal electron acceptor, and it has a 0.82 volt reduction potential. It's really large. Okay, so when we start to look at this, okay, heme is in complex 4, heme A is in complex 4, and it's going to have the highest reduction potential. Okay, B's would be typically lowest, okay, and then C's would be in between. Okay, right. We could say the same thing for iron sulfurs. The iron sulfur centers that are found in complex 1 are lower in reduction potential than complex 2, 3, and 4. Okay, NADH, of all of the things that we've talked about, has the lowest reduction potential, followed by FMN and then FAD. Okay, and then we've got the iron sulfurs and the cytochromes mixed in between. Okay, all right. So let's go ahead and stop right there. All right, we will come back. We'll start at complex 1 on Monday. Not on Monday, on Wednesday. You're thinking, oh, we get the rest of the week off. Okay, good. Wednesday.